All right, let's dive right into this explainer. Imagine you're walking down a dark engine room corridor. Behind a locked steel door sits a single piece of hardware that literally decides whether your massive marine vessel sails or just sits completely dead in the water. Today, we're tearing into marine medium voltage switchboards. This is the absolute nerve center of a ship's electrical grid. We're going to break down exactly how they're sized, what they're built out of, and how they are engineered to survive some truly catastrophic electrical faults.
Because here is the bottom line. If this board fails, the ship dies. Period. We're talking about one single medium voltage switchboard feeding absolutely everything. Your propulsion, your thrusters, the entire hotel load. Every single amp flowing through the vessel passes right through it. If you get the sizing wrong, nothing downstream works. It really is the ultimate beating heart of the power distribution network.
Section 1. The heart of the ship and 8 critical variables.
So, how do marine electrical engineers actually go about sizing this life-or-death hardware? Well, for practical engineering, you have to nail these 8 exact variables. Choosing the right switchboard, whether you're running at 3.3, 6.6, or 11 kilovolts, means locking down your supply voltage, continuous current, short-circuit duration, switching frequency, supply frequency, ambient conditions, and, of course, the physical footprint. But listen, when things go south and a violent fault occurs, 2 of these suddenly matter way more than anything else. Your maximum short-circuit current, which defines the sheer thermal and mechanical stress, and the short-circuit duration.
And that brings us to a terrifyingly brief window. 1 single second. That is the standard short-circuit duration. It tells you exactly how long your switchboard has to physically survive the extreme thermal and mechanical violence of a fault before the circuit breakers can manage to clear it. Now, 1 second might sound fast to you, but trust me, in electrical terms, an arc fault raging for 1 full second is an absolute eternity for copper and steel to endure. Okay, let's test this in the real world with a quick scenario. A yard gives you 2 switchboard quotes. They have the exact same current rating and the exact same voltage. One is rated for a 40 degrees Celsius ambient environment, and the other is rated for 45 degrees. Which one do you pick for a Gulf of Mexico FPSO? Think about the actual physical environment this board's going to live in and how that completely alters your engineering calculations. You always, and I mean always, choose the 45-degree unit on the right. Offshore ambient conditions are absolutely not just a footnote on a spec sheet. They are a massive design driver. Heat, humidity, and salt spray to grade insulation and contacts far faster than any onshore installation. Your actual switchboard room temperature, sitting right under that tropical sun with an intense machinery heat load, is going to run so much hotter than any temperate climate default. And that right there is exactly why marine specs carry much harsher D-rating than industrial land equivalents. Moving on to Section 2, identifying switchboard families and the obsolescence risk.
If you walk onto any vessel that's over 10 years old, there is an incredibly high chance you're going to be staring at switchgear that literally nobody manufactures anymore. Take a look at these 5 families that totally dominate marine medium voltage installations from ABB. Just check out that status column. The MH12S from Finland, discontinued. The ZS1 out of Germany, discontinued. The Universi and Unisave from Italy, both discontinued. 4 out of the 5 major types are completely out of production, leaving just the modern Unigear as current. That is a pretty stark reality for engineers trying to maintain these floating power plants.
So, the golden rule here is this: read the nameplate before you order anything. The model ID is stamped right there on the front of the board. If you're commissioning a vessel built in 2004 and you find an old Universi board, you can't just order OEM spares off a shelf. Reading that nameplate is your ultimate reality check. It tells you right away if you're going to need to source parts through secondary markets, plan for some compatible retrofits early, or, in the worst case, get ready to cannibalize a sister vessel.
Section 3. Inside metal-clad construction.
Let's mentally open up that metal door. I want you to imagine an apartment building. If one unit catches fire, thick concrete walls guarantee that the fire absolutely cannot spread to the unit next door, right? That is exactly what metal-clad construction does inside a switchboard. It utilizes rigid steel walls between the internal compartments. One fault equals one compartment. It guarantees that a failure in one zone is totally isolated and cannot destroy the whole board. Let's break down those firewalled zones really quick. Every metal-clad cubicle is built out of 5 standard physically isolated compartments. First up, you have the main bus bar compartment, which houses the raw copper bars.
Second, the circuit breaker compartment holding the withdrawable breaker right on its truck. Third, the cable terminal bringing in your feeders. Fourth is the secondary equipment up top, dealing with all the delicate protection relays. And fifth is the operating unit handling manual control.
Now notice how the physical hardware inside that first compartment scales directly with the current. The busbar compartment is definitely not a one-size-fits-all deal. A standard 1250 amp board typically runs 2 copper busbars per phase, but the second you step up to a 1600 amp rating, boom, you immediately need 3 busbars per phase. The physical copper literally has to scale up so it can carry that extra electrical load without overheating.
Which brings us to Section 4, Surviving the Fault and Safety Interlocks.
So, what actually happens when a violent arc fault ignites right behind that metal door, with a technician standing just a foot away? Consider this very real scenario. A tech wants to rack a breaker out with the compartment door open, deliberately bypassing the interlock just to quote-unquote save some time. What is the actual risk here? I want you to seriously think about the massive safety implications of deliberately ignoring the board's built-in physical defenses.
Well, the answer is pretty much everything is wrong with this. Bypassing that door interlock instantly removes the arc fault protection guaranteed by IEC 60298. Racking with the door open completely removes your metal firewall. If an arc ignites while you are racking that breaker, which, by the way, is exactly when a mechanical failure is most likely to happen, there is literally nothing between you and thousands of degrees of superheated plasma. Doing this bypass is the single most common way engineers get severely injured or worse.
So as we wrap up this explainer, I want to leave you with a lingering thought. A single board holds the power to keep your operations afloat or leave you completely dead in the water. Do you know exactly what hardware is inside yours? Because it's this invisible, precise engineering, from properly derating for ambient heat, to tracking down discontinued spare parts, to respecting those critical metal-clad firewalls that truly prevents disaster at sea. The more you know about what's behind that steel door, the safer your ship will be.